Okay, in the last couple of problems, we've looked at two interacting object scenarios. One was the modified Atwood's machine, where we had a mass little m being pulled with a rope over a pulley by a mass big M. And we had the basically very similar scenario of two masses with a pulley, little m, and big M. So same basic scenario. In both cases, we wanted to find the magnitude of the acceleration. Okay, well, we related some constraints. We saw that the acceleration of little m in the x direction was the same as that magnitude we were looking for. This is using our sort of standard coordinate system. And the acceleration of big M in the y direction was equal to negative a. Similarly, over here, we found that the acceleration of little m in the y direction is a, and the acceleration of big M in the y direction is negative a. And that was using this coordinate system. Now, that's fine. But what if there was an easier way? I don't know if this is easier, but it is faster if it doesn't confuse you too much. And the shortcut is to use the fact that if we look at only the external forces on a system, we can find the acceleration of the total system with F equals ma, but with the looking only at the external forces, looking at the total mass, and then that would relate to the acceleration of the system. The reason why this is a little bit tough right now, the way we have it written, is that the acceleration of the system doesn't seem super well defined, right? We have an acceleration in the x direction and the negative y direction here, positive y here, negative y over here. And so what does it mean to have a single vector represent the acceleration of the system? Well, this is what it means. What it means is you change your coordinate system. And your coordinate system folds over the pulley, like that. I know, this looks crazy. And here, the coordinate system folds over that pulley, like that. So, anything that's pointing this way up here is the positive y direction. Anything that's pointing this way over here is the positive y direction. Over in the other problem, anything pointing that way is positive y. Anything on this side pointing that way is positive y. I know this seems like cheating. It comes from the fact that our motion is still linear, right? Every time big M moves down a little bit, little m moves, in this problem, moves to the right by the same amount, and this one moves up to the same amount. These aren't actually independent coordinates. So, if we look at the standard Atwood, so that's the one on the right, we only have forces in the y direction. Right? And a great thing now is that the acceleration for every object in this is in the positive y direction. So in this coordinate system, a little my is just a, and a big my is just a. They've got the same acceleration. So what are the net forces? And remember, these have to be external forces. Well, the tension is an internal force, right? It's between, it's conveying a force from big M to little m. So it's not an external force. The only external forces are gravity pulling downward on big M, but downward is in the positive y direction for big M, And we've got gravity pulling downward on little m, but on little m side, downward, is the negative y direction. Well, that is equal to the total mass, little m plus big M. And the acceleration of the system is what we just called A. So there we go. A is equal to big M minus little m over big M plus little m g. Boom, 2 lines. 3, I guess, if you count writing out the equation. Same sort of thing with the modified one, which is on the left. We've got an external force of the mass big M pointing down. Right. We do have external forces on little m. We have the weight of little m and the normal of little m, but those already cancel out. So those external forces on little m balance to 0. The tension is an internal force between little m and big M. So when we write sum of the forces external is equal to mass total times acceleration of the system, there's only one external force, big mg, and it's in the positive y direction on that side. What's the total mass? M plus big M. The acceleration of the system's A. Acceleration is big mg over little m plus m. Boom, 2 lines. Okay, and the next one we're going to add friction.